simple arrangement that a NAND gate is driving a NOR gate, and NAND gate output is there is a voltage level called VOH. Now you know the word YO has been attached here because the output of the gate, and the word I is attached here because the input of another gate. High word is used because now we are considering that this gate is driving one, this gate is receiving one. Okay. So now in this case VOH is actually the voltage available here, VAH is the voltage. These are the ranges. VOH will be ideal, VAH will be worst case acceptable. That difference is nothing but we call noise margin. That's all we know. Now coming to currents, the current that is produced by here is IOH. Okay, and the current that actually is required here is IAH. Now this is not all the time compulsory that the driving gate will be sourcing and the receiving gate will be sinking. It may not be compulsory. There may be some logic families where it is reverse. The driving gate will be sinking type, whereas the receiving gate will be sourcing type. You understood? Yes. But whatever it is, the kind of fan out, as we discussed yesterday, comes like this. If let us say this is requirement is 1 milliampere, and the maximum this requirement is 10 milliampere, so fan out becomes 10. Because this requirement is 1 milliampere, whereas this fellow has to drive 10 milliampere. At the most it can drive 8 milliampere. So 10 like this parallel can happen. Okay. Now same story for the load. Now whether low is decided fan out or high is decided fan out depends under both conditions what becomes worst case. Got it there? For example, let us say this gate is able to drive 10 gates for low, but it is able to drive only 5 gates for high, let us say. But which one you will consider? You have to consider 5 only. Because a gate, once you form a circuit, it has to work for both 1 and 0. Right? So worst case out of these capabilities decide basically the fan out. That is what we are trying to summarize here. The maximum number of standard logic inputs that an output can drive reliably, that is what actually fan out. Also known as a loading factor. Okay. Now let me also tell you one important thing, like when it comes to ASICs and also FPGAs, we use one word called clock tree. Okay. Clock tree insertion, clock tree management, clock management. These are the important phases in ASIC backend. Okay. Of course, in front-end also there are some directives. Through your vehicle where you are code, you can give directives. Through your coding style, automatically the tool will figure out what is clock, what is reset, etc. etc. Now, why I am talking about that now is that if you especially talk about FPGAs, let's say if you look into the FPGAs now, it's applicable to ASICs also, but I am going specific to FPGA example. See, there is something called clock buffer, okay, and there are certain units called clock management units, DCM. So if you use BCMs, and if that clock is distributed to your entire module, your module may be very big module, maybe 2000 lines of BHDL code, that might be occupying 50% of the chip. Okay, you would find, okay, you would find that, I'm coming, just wait one minute. So you would find that the total logic will work correctly. You give all the multipliers, adders, all the inputs, output you find correctly. But what, let us say, if you don't use this BCM, okay, some other clock, let us say, which you generated out of your code. How generation is what? In your code or your code, you said that clock is assigned to 0, and after some rising clock, you create as a data, and that if you drive with this one, your total code will misbehave. What is the reason for it? Reason is very simple. In FPGAs and ASICs, when we say clock tree and clock lines, those are the lines, those are the, in terms of physically like metal widths and all, and in terms of the gates and the sizes of these, source, drain and all, to give more amount of current they are designed for. That is what actually the whole load comes over here. Okay, in digital circuits, the clock fellows are the highly loaded. Why? See, what happens is, full adder, half adder, and all circuits, AB, out the full adder goes to some other thing. So, for a particular signal, if it is going to only 4x4, that will happen. But clock is something which goes to all the registers. So, clock should be the fellow which is with highest driving capability. That is what. Why people talk so much about ASIC clock tree insertion, clock tree management is, clock trees are actually, you are used very carefully. Because they are occupied resources. They will take more area on silicon. If you are running a, let us say, metal 4 clock, that will be very wide. Got it? So, and that you have to use carefully. Okay? Just give me a minute. Okay, let's call loading factor. So, I am just telling you the importance of clock in this case, because in ASICs and FPGAs, certain lines are given explicit capability of driving more number of signals, like clocks, enables, etc. etc. Okay? You will anyhow practice using them in FPGA course later. Okay? Now, related to current parameters, these are okay. That's what we are discussing now. This is something which we are discussing now because there is a reason for it. Okay? Especially about the speed, performance, we will have a separate discussion. But our concept here is the current indirectly plays a role in terms of propagation delays also. What do we mean by that? Look at this one. Let us say there is a gate and there is another gate. This gate will have some input capacitance. Okay, and this gate is going to, let us assume it's a positive logic. Okay, and the kind of model that is, when this is going to drive one, it is going to send current and it is going to sink current. And in CMOS kind of logic families, this fellow is not even going to sink current. But indirectly it is the effect of sinking current only because there is an input capacitance of it, which is to be charged. So now you look at, let's say if you pump 1 milliampere current, okay, let's say this capacitance is 10 picofarad. The 10 picofarad to reach 1.8 volts VDD with 1 milliamperes of drive, it takes, let's say, T1 amount of time. Instead of 1 milliampere, if you have 10 milliamperes of drive, it will take much smaller time. Maybe you can approximate it to be 0.1 times of T1 to reach same 1.8 volts. You understand? Now you see, I mean, why we are talking about this one is, let us assume that this particular fellow fan out is 10. Fan out is 10 in the sense, this can maximum deliver 10 milliamperes. If there are 10 devices, each one will be getting only 1 milliampere. And each one input capacity is 10 picofarad. So all fellows will take T1 amount of time to reach here, to get that input logic. But if there is only one gate, you see, then this gate will be able to switch faster. Got it? This gate will be able to switch faster. There is an important point from here. I am making a reference in my next quote we are going to discuss. That when we say that there is an ND-gate delay precisely we cannot tell like one number. Because this ND-gate may be driving by another ND-gate, which may be driving only this ND-gate or may be driving parallelly another 1 or 2 ND-gates. So in that case, if it is parallelly driving 3-4 ND-gates, this may take 10 nanoseconds. If this ND-gate is driving this ND-gate only alone, it may take 5 nanoseconds only. You understand? So what it means, that's so in our next module where we are talking about precise characterization of ASIC timings for sequential logic and all. There, for a gate, we talk about 2 numbers. It may take any time between 5 nanoseconds to 10 nanoseconds to get the output. Understand? This becomes a major source of glitches in combination logic circuit. We will study all these about glitches and there is something called contamination delay, all that we are going to study. But the bottom, the base for all of this actually comes from here. Okay? A fan out is going to tell that under some guaranteed amount of time T1, it can parallelly drive all the time. However, if it is not driving all of them, it is driving only some of them, it will take lesser time than T1 only. Got it? So that is the reason the propagation delay also is discussed in addition to the driving capability, because both as a combination that becomes a trade-off. Like you want to have more fan out, you may be having more fan out at the expense of taking more delay. Got it? See, same current is there. This mainly becomes the issue in CMOS. Because in CMOS, it is like this. It won't require any current practically for the gate to switch. But the only thing is, depending upon the current there, it will take more amount of time to actually switch. Unlike in TTL, DTL and all, there is no absolute current minimum that you need to maintain. Got it? So in CMOS, no problem, you give even 1 nanoampere also, gate will switch, it will switch out in, let us say, 1 microsecond. Got it? So usually in logic families, when people talk about driving strength, it also is tagged with actually the delay, the speed. So that's the reason this slide is discussing here about propagation delay. I guess this definition may not be a new definition for you, you know that the input is changing, output is changing. An example of inverter has been shown in the waveforms. When input to output 50% to 50% change delay is what we call it as a propagation delay. And that propagation delay, in the context of when output, these definitions are with respect to output. LH and HL are with respect to output. When output is going from low to high, it is called TPLH. Okay, so look at if this is actually input and this is output, which is TPLH. This one is TPLH. T propagation delay from low to high, output is going low to high. And TPHL is this delay when the output is going from high to low. That also, they also need not be same. Okay. Anyhow, why we are discussing them here is, usually, I think it's the next slide. Yeah. Usually, the important thing is we talk about the speed power products. How? You may ask how power is coming into the picture. See, power comes because, you are using some amount of current to charge a capacitor to some amount of voltage. Then there is energy spent that is there, that is half CV square. Isn't it? So that energy spent in some amount of time is nothing but the power. So it is something like this. When you are trying to compare TTL, CMOS, ECL and all, just simply you say CMOS fan out is more. That may not be good characteristic method. Why? Because CMOS fan out is more, but each gate to switch takes long time. So usually what we do, we take a product of power that you are burning and the delay. Speed power product, that is what actually you need to achieve. You want to have a reduced delay and reduced power. Let us say, my delay is very, my gate is switched very fast, but I want more power. That is also not good characteristic. You understand? You say that actually I got very low power, but the speed is microsecond. That is also not good characteristic. So we will define something called delay, which is nothing but the delay in nanoseconds or microseconds, product with power. So this what we call as speed power product. Actually, more precisely should have been called delay power product. And tell me what is desirable? You are looking for minimum or you are looking for maximizing this value? Minimizing this value. You want basically the smallest delay and the smallest power. Okay, in some case, let us say ECL logic family is there. In ECL logic family, delay is actually very, very small because ECL is the fastest logic family, emitter coupled. Okay, so fastest. But where you are paying for power. So when you do product, this level becomes again comparable to TTL and all. So in general, when you want to talk about comparing 2-3 logic families and comment which one is good, it is not appropriate to only take delay or only take power. So take a product of them and define. Okay, and this parameter among multiple logic families, whichever is actually having minimum, that can be considered a good logic family for that application. You understand? Okay. Now, when you want to comment on TTL and the MOS variance, okay. Now, in case of TTL, we usually refer as VCC, that nothing but logic 1. In case of CMOS and all, we usually refer as VDD, this one. So, power dissipation is decided by ICC and VCC case if it is TTL. Okay, collector current, that how much you are drawing. So, average current, so usually we do calculation like this, because there is an amount of current that is involved from low to high, there is involved current from high, there is a current pumping, okay, there is required when the output is low, and something the output is high. But in general, a gate is maintained what value we don't know. So we assume 50% probability for 1, 50% probability for 0 and take an average of it. That average product we consider as a power. Same thing for CMOS also. Okay. Now, practically that is not the case. See, practical, what is the practical? Instantaneously that is not the case. More precisely, I want to change your statement. Instantaneously, this is not the case. If you want to say instantaneously means what exactly at this instant of time, what is the power consumption? In that case, you have to see at this instant of time whether the logic gate output is high or low. If it is high, you use only ICCH. Don't take average. If it is low, you use only ICCH. But in general, when you want to characterize, see, in general, when you want to characterize, there you know some, it may be 1, it may be 0. So what we generally consider is whenever we don't have any special data about how many, what are the chances of becoming the output to be 1, what are the chances of becoming output to be 0, we take 50% probability. Not only that, in so many other future calculations also, let us take full level is there. For full level, how many input combinations will be there? 8 combinations will be there. 0, 0, 0, 0, 1, 0 and all. Now question comes, 0, 0, 1. What is the chance of having 0, 0, 1 input combination? If we don't know anything, we assume all are equally probable. If there is no bias on the inputs here, we assume unbiased input in the sense all inputs are equally probable. Then we assume 12.5%. How 12.5? 100 by 8. 12.5% of time, the input is likely to be 0, 0, 1. Let us assume for each combination we have a different amount of power. Then we take average and solve. Same thing here. Okay. Now coming to noise margins. Noise margins we are aware of. Okay. Noise immunity. That is nothing but noise margin. Immunity. How much it is immune? To what level of noise this digital logic is immune? Got it? Okay. Now, what happens if noise causes the input voltage to drop below VIH minimum or rise VIH? That's what. So up to this level there is no problem. VIH is actually minimum output voltage that I will go at the output. VIH max, this one is actually this is not a precise statement. This is maximum. Maximum input voltage that this logic. Sorry, that is minimum voltage. I am also getting confused. Let me draw the diagram, or it is there in the next slide. Yeah, this one. So this is the driving logic output. This is the other logic input. When the driving logic output says output low means it is going to give this value. The reading logic, okay, will have a little bit higher threshold. So this will be maximum, obviously. Okay. In this case, we have to consider VOL maximum only. Correct. Okay. But usually what happens, when it comes to CMOS and all, these will be fixed values. VOL and VOH will be fixed values. But again, yesterday I was trying to show an example of fanning example. Fanning. How many gates can be there? Okay. Let's say when the device is almost going close to the peak fanning, the output voltage level won't be the optimal voltage level. There will be again variation. That is why I think the precise terminology will use maximum, minimum. That difference. So obviously, if anything in this zone is the invalid zone, indeterminate zone, and what is the condition that we discussed about? It is called metastable condition. So when circuit goes into metastability, what can happen?
More delayed output might be.
Yeah, there are two things that are possible. One, the logic itself may come wrongly. Second, whether it is correct logic or wrong logic, it takes more time to set it. Okay. Now, a little bit more about this current discussion, current sourcing and sinking. We were discussing a similar example last time. See, let us assume that is a kind of NAND gate where both inputs are low, output is obviously high. So high means it's a kind of TTL example where it is seen through VCC, through some resistor. So this is a current. Okay. And this fellow for the gate, this is actually sinking. So this is a sourcing, is a sinking. Okay. In other case, where actually these two are high and these are low. So in this case, what happens? This is actually seen, output is low. In the sense, if it is a TTL logic family, the transistor is in saturation. Then through transistor, through transistor that collector emitter saturation junction, this current has to sink. So maximum current handling capability of the transistor will become a limiting factor in this case. So for the fan out, this could be limiting, this could be limiting. Whichever is minimum, we have to consider that. Okay. Yeah. So coming to kind of summary of TTL. Okay. So it's a transistor logic, kind of NAND gate. This is an NAND gate. Okay. How it works? Just for the sake of getting a feeling of logic, something we are studying about it. Otherwise, our major concern is not to learn in and out of this. Okay. No. So how it works is, see, these two are basically the junctions. Okay, these are base, emitter, collector. If you apply high voltage here, let's assume A is high, B is high. When both high voltages are applied, these both junctions are reverse biased. In that case, current finds this path. So this goes into forward bias, and subsequently this also goes into saturation, and finally this will be zero. Okay, actually it won't be zero. It is supposed to be VCE sat, saturation voltage of this one. So this fellow is going into deep into saturation. Okay, and this will be basically this one. So there is a name given for this, is called total pole tail. Okay, I am not very sure, it's a long time back I analyzed this circuit. I don't know whether this pair or this pair, one pair is called totem poles. One goes on, other one goes off, something like that. Concern is, I mean, what you want to look at is, we were talking about the other case, when in the previous this one, when in this case, when this fellow is giving 0, isn't it? What will happen? Now you analyze this context. When you are giving 0 here, now see, this is what a forward bias is. This is what a forward bias condition. Now current will come from this direction. And another, a gate like this only is driving this one, means for the driving gate, this terminal is what connected here.
Yes.
The current is going where? It is going to this one. Understood? So that is what broadly what we discussed so far. It is detailed explanation of it, but that's not very much important for us. And now there comes this one. Okay. So coming to TTL, even though it's little out of scope, it's a word that it's good to know this history of it. So Texas Instrument is a company in 1964. They introduced the 54 series and 74 series TTL chips. I think you might have done your ECAD lab, something like that. 74 LS, write the equivalent DSL code like that. Okay. If I remember correctly, 74 happens to be the commercial series and 54 happens to be little temperature grade or industrial grade series. Same functionality. That's what they mean. So what are they? Like something like they give an IC. Okay. Some, let us say some 74 LS, something like the IC. It will have pins, something like this, and inside the pins there are some gates, few gates, NAND gates, NOR gates, something like that. So when you want to relate a Boolean function, take this kind of ICs, 5, 6, make a PCB. Each IC might be deriving, some part of the Boolean function, and this IC output current to next IC like that. This is all 1964 terminology. Okay. Now nobody does like that. Today we go to FPGA, which is going to have millions of gates like this. You can configure. But anyhow, that is what. But TTL, even though we are not going to use TTL for the logic inside the IC, okay. But for interfacing, that is one IC driving another IC, TTL is one of the standard. Okay. Because within the silicon, okay, the important quality that we are looking at is the density. That is, we should occupy smaller silicon area and realize a Boolean function with extra doing planning, panels and delays and all. CMOS proves to be the best order. Actually, NMOS and PMOS are the best. In case of CMOS, area is bigger, but NMOS, PMOS have power problems. They burn more power. So when we talk about the speed power product, CMOS becomes actually good choice. So CMOS logic for analog and digital variants are the dominant on-chip design logic factor. That is on silicon. So in our subsequent topics, we will talk about only CMOS. We will not talk about the others. Okay. However, when it comes to one IC output driving another IC, something like that, then some logic summaries are still existent. TTL is one of them. Okay. TTL is existent. ECL is existent. Okay. There are some variants of DTL which are called HTL, HSTL, something like that. They are also existent. Okay. But TTL is very popular. Okay. So in this context, a kind of comparison of TTL, what is known just for your reference to understand the numbers. We are talking about the delays order of nanoseconds. We are talking about the power dissipation order of milliwatt. That is what the potential bottleneck of TTL. Whereas if it is CMOS, okay, the near would have been slightly more, okay, maybe 15-20 nanoseconds, but the power will be order of nanowatt. That is where the CMOS becomes, very useful. Determining the fan out we discussed yesterday. That is what about take, when the output is high. That is IIH, IOH, that is one criteria, one constraint. Output low is one constraint. Whichever becomes more dominant problem, you have to take that. Let's say output high case decides fan out to be 6 and output low case decides fan out to be 3, you take 3. That's all. Now coming to MOSFETs, okay, we'll be talking more and more about MOSFET. You know that we have P-channel MOSFET, N-channel MOSFET. If there is P-channel MOSFET, what is the drain type? In P-channel MOSFET, what is the drain type, drain and source? What is the material type of drain and source? Last session we were having a discussion of the mass cross-sectional view. Now, in a P-channel MOSFET, what is the nature of silicon material, the drain and source?
Highly doped.
Highly doped. What type highly doped? In a P-channel MOSFET, what type? They are P-type. P plus. Do continuous reading. Okay, what we are discussing. That's what. I will do all supplements. Like I am not giving the slides now. Now itself I will hand over the slides to you and also It will become a formal activity from now onwards, handling daily evening slides and also the what is called video, which is actually called. Okay, now CMOS becomes actually a kind of variant of PMOS NMOS combination. Okay, we learned with CMOS inverter last time. We are going to learn further. Okay, now coming to typical numbers. If you are looking at an N-channel MOSFET, it will have what is it called, gate to source voltage. It gives 0 volts. It's like an off transistor. And what the resistance of that order of 10 giga ohms, very high resistance. It is equal to open circuit. It's equal to open circuit. Okay. Whether that open circuit is high impedance or not depends what the other side it is. Got it? Because you use the word high impedance, I should explain this. For example, in case of CMOS, simple CMOS won't be able to create high impedance. What is required to create high impedance we will study later subsequently. A simple CMOS case, what happens is, see, if the PMOS is off, we are going to offer 10 giga ohm impedance. It's like an open circuit, open switch. When this is off, this will be on. So that will be having only 1 kilo ohm. Got it? So these are actually the on resistance, we call it off resistance. So you never get actually a high impedance in a simple CMOS inverter. So that high impedance will do something that we will study later. Okay? These are some calculations of it, and how you get basically CMOS gates. Let me tell you. Have you studied this concept somewhere in your academics? Pull-up network, pull-down network and all? So you can visualize a simple, not only CMOS. There are two types of logic family, logic design slides. One is called transmission gate logic, other one is called restoring logic, right? We will have a formal discussion separately in our next module. But in simple words speaking, a digital circuit can be seen like this. You have inputs fed here, optional. Maybe in some logic family there may not be inputs here, there will be only inputs here. In some logic family like CMOS, both inputs will be here and here. So how we design our logic is, pull down network is something which will pull down this node to ground. Means if pull down network is on, output is 0. If pull up network is on, output is 1. To ensure that there is no direct path for current, so that the power limitation, power difficulty is under control, we design our circuits in such a way in CMOS that when pull up network is on, pull down network is off. When pull down network is on, pull up network is off. That's how. So either you have path to VDD or you have path to ground. Understand? So now when it comes to the simple way that how we design is, when you want to design the NAND, we have to put the pull down network as a series and pull up network as a parallel. You notice that the pull down network is 2 NMOS transistors, that is these two, and pull up network is 2 PMOS transistors. When you want to maintain output 0, these two will be like both should be 1 to take 0. Isn't it? That is what NAND configuration, right? All inputs should be high to begin. That's what. When all inputs are high, then only the pull down network, all NMOS will be seen through ground output. Same way, NAR is reverse. To realize NAR logic, all inputs pull down network should be parallel, pull up network should be in series. Okay, now this is another topic which we are going to discuss next year. When we are talking about how to interface one chip to another chip. Okay. No, one thing is like, as long as a TTL chip is there in TTL chip, there is nothing great. Okay, the same issues which you talked about, fan in, fan out, same thing can be applied here. Only thing is, now it is not the on-chip connection, it is off-chip connection. The PCB track length, their resistance, also you have to slightly account there. Okay, because see, ideally on-chip fan out is 10, but when it is off-chip on PCB, fan out may not be 10. Because the track length on PCB will have some resistance. Only that much will differ, nothing else. But usually what happens, when it is off-chip connection, digital connection off-chip, it is quite likely that it is a mixed logic family. Driving could be TTL, driven logic could be CMOS, or it could be other. In that case, what are the issues? If TTL is driving CMOS, most of the time there is no problem with current requirements. Right? CMOS does not take currents. In case of CMOS, it does not have an absolute current threshold that I need this much of minimum current to switch. No. You give some current Based upon the current that is due, the input capacitance charging time will only differ, but it will change. Okay? That's the reason no power with current requirements. Now coming to VOH minimum of TTL. What is VOH minimum? VOH output high, minimum value that you give of TTL is low compared with actually VOH minimum of some CMOS series. Use pull-up resistor to raise TTL output voltage. Something interesting which we have to learn. Now this is the correct condition where we learn about what is called pull-up resistor. What is called pull-up resistor. Now see, we have a TTL gate. Let's assume CMOS. Now, sometimes not CMOS. In our case, it is a TTL. It's a gate which is producing output voltage. What is the output voltage? We are concerned about VOH minimum. Isn't it? Look at our diagram. So these are the inputs. VOH minimum, VOL maximum. VIH minimum, VIL maximum. This is what the difference we are concerned about. So driving gate is VOH. Its minimum value is not going to be important. Let us assume that this minimum value is small, and because of that you have a compromise on the noise margin with respect to CMOS. What is that you can do? See, what you can do when this is high, you can actually have a mechanism here. This is called pull-up resistor. See, what this pull-up resistor is going to do? Let me take an example. This NAND gate is internally powered through, let us say, VCC is equal to 3.2 volts. Whereas this VCC is equal to 5 volts. So let's see what will happen. See, this is what the internal circuit. Output is high means this is off. When this is off, there is no current path. Here, there is only current path between these two. Like let's say this is RC1, it's a RC2. Now effectively what happens is, if this is 3.0, this is a 5 volts, you will see 5 volts here. So what we have done by adding this pull-up resistor and pull-up this one, you are able to give basically this one. And not only that, see, you may wonder like, what if they just want to give 5 volts? The intention is, by adding this additional, this one, you are able, now what will be the major challenge? This is one. This will be driving something else, right? So the driving current not only comes from this VCC but also comes from this one. So now what is your drive state going to increase? That is what the purpose of pull-up. Okay? So many times when you are taking ICs and doing the boards, the IC manufacturer will tell the actual internal strength, the driving strength of this one is like this. When you want to drive more capacity load, add a pull-up resistor and connect to VCC of 3.3 or 5 like that. That is what the purpose of pull-up resistor. So TTL driving high voltage CMOS. There are other variants of high voltage CMOS where that voltage levels are very high. Then some buffer and all. It's practical stuff which is not required. In principle, what is the idea is your VOH minimum is not suitable. You want to lift it. Then add a pull-up. Same way your VOH maximum is not good. It is going very close to this. So noise margin for 0 is compromised. What you have to do? You have to add pull down resistor to ground. Very simple. Okay. Now if it is CMOS driving TTL, okay, high state, when the output is high, indicate no special consideration the high state. Okay, because what happens in case of CMOS, this will be pull-up network, this will be pull-down network. When output is high, directly there is a VDD and there is a current that is coming. Okay, and present day CMOS technology, the arm resistance won't be under kilo ohm, so it is much lesser than 2 ohm, 1 ohm like that. You have plenty of current, whatever you want. No problem. Okay, and low state depends on actually the series use. When the output is low, depending on which series it is and what is the arm resistance, off resistance and all, what is the drop, all that. Okay. Now, if you want to go in depth, why you are so concerned about low and high is, in case of TTL, recollect that there is a base emitter junction. Got it? So the emitter needs to be some 0.6 volts lower than the base to become basically that 100 there is 0. There it becomes a special problem. But output high, Okay, it's not a special problem because already it is above base limit tension. Even if it is little above or it is fully above, still it will be considered as a 1. That's the reason we are talking about. Okay. Anyhow, this much is enough for basically we will teach you to understanding here how these logic families, concepts of these noise margins or whatever it is, on chip or off chip, how they are going to become one. Okay. So we will continue tomorrow. We already got the date for the other things. Yeah.